Hello all. Today we will be discussing the next topic in the third module, that is the combinational circuit. Yes, so if we consider digital circuits, logic circuits, we have two types of main categories. The first one is combinational circuit and the second one is sequential circuit. All the logic circuits can be classified either as combinational circuit or sequential circuits. Let us understand the definition of combinational circuit and sequential circuit. So if we consider the combinational circuit, so it is a logic circuit, it is a digital circuit in which the output depends on only the present input. The output depends on only the present inputs. Okay. Coming to the second category, that is sequential circuit. So in sequential circuits, the output depends on present inputs as well as previous outputs, so which are nothing but state of flip-flops or memory elements. Yes. So this is the definition of sequential and combinational circuit. So combinational circuit is the one in which the output depends on only the present inputs. As soon as the input changes, the output also changes. It will not be having any dependency on the previous inputs or previous output. Okay. Therefore, so in this circuit we will not be having any memory. So in order to store the previous contents, we will not be having any memory because it is not having any dependency on the previous inputs. So coming to the second type, that is sequential circuits. So the output is depending on present input as well as the previous output. So the previous output is nothing but the content of the memory elements. Therefore it will contain the memory elements which are nothing but the flip-flops. Okay. So this is the basic difference or the basic definition of the combinational circuit and sequential circuit. Now, so we have only combinational circuit and we have very simple example, that is adder. Let us see few more points about the combinational circuit and let us understand so what is an adder and what are the different types of adders we have. Yes. Now, combinational circuit, if you consider, it will be consisting of three parts. One is input, output. So we will be having n inputs. Okay, let us consider there are m outputs and in between this we will be having combinational logic. Combinational logic which will be consisting of logic gates. So this logic will be made up of some logic gates. So it is going to accept n inputs and it is going to we are going to apply n inputs to the logic gates which are present inside this. So if it is an adder circuit, we will be having some circuit. If it is a multiplexer circuit, we will be having some combination of logic gates, that is connection of logic gates. So we are going to have some logic gates here, so which will be accepting the input and then according to the connections what we have made, how the connections has been made, so according to that the output will be produced. So this is the basic block diagram of the combinational logic. So for any example, for any combinational circuit, we can write such diagram. So as I said, if I consider adder, so that too half adder, let us see what is half adder and what is full adder later. Now if I consider a half adder as an example for combinational circuit, then we are going to draw like this. So this is half adder, and inputs to half adder are A and B and output is sum and carry. This is how we are going to represent. And so to be more specific, let us represent the circuit see. So this is how, okay, the half adder combinational circuit will be, okay. Yes, here you can observe, so we are giving 2 inputs and we are obtaining 2 outputs, and those outputs are obtained by using logic gates, so which are, okay, obtained using the logical expressions what we write for the truth table, okay. This is about the combinational circuit. Combinational circuit, the inputs, n inputs whatever we have, all these are the logical 1 or 0 values, and the m outputs whatever we have, these are also either logic 1 or 0, and each and every m output whatever we have will be having a Boolean function. So it will be having an expression, so that expression is obtained by writing the truth table. Okay. Now let us understand the design procedure of this. So before moving to the design procedure, so we need to remember one more point, that is the n inputs whatever we have, so it may appear either in its original form or in complement form. So we may have 2 wires, so to obtain the complement as well as the original signal. So sometimes we may have an expression which does not contain any of the complements. So if it contains the complement, then we will be having 2 wires for each of the input. Okay. So this is about combinational logic. Okay. Now let us understand, so what is the design procedure we follow in order to obtain any combinational logic circuit. So if you consider the combinational logic circuit, the very first step we follow, okay, in the design procedure is that, so the problem statement, we are going to get the problem statement okay. So from the consumer, okay, so from the customer we are going to obtain the problem statement. Once we get the problem statement, we are going to write the truth table for this problem statement. The second step is to, okay, before writing the truth table, first we need to identify the number of inputs and number of outputs. So once we get the problem statement, we need to go through the problem statement thoroughly and understand what are the inputs to the circuit, what are the outputs of the circuit, or what are the inputs we are supposed to give to the circuit, okay, and what are the outputs we are supposed to get. So we have to decide upon, okay, the inputs and outputs. So that is the second step, identification of inputs and outputs. Next, third step is to assign some variable names. So usually we assign some variable names to input and outputs. Okay, inputs and outputs. So this is the third, okay, step we follow. Next is, after this, okay, so we are going to write the truth table. So what is truth table? Truth table, okay, so is the one in which we are going to assign logical 1 and 0, okay, to both the inputs as well as the output. In the sense, first we are going to write all the possible combination of inputs. Say for example, if we have 3 variables, 3 input variables, then we are going to, okay, write the 2 power 3, so which is equal to 8 combinations starting from 0, 0, 0 to 1, 1, 1, okay, 0 to 7. We are going to write all the 8 possible combinations, and output value is based on the problem statement. So we are going to identify whether we have to assign logic 0 or logic 1, okay, from the problem statement. And sometimes, so they may give or they may not give some of the input combinations, okay. So in such case, what we are supposed to do is, we are supposed to consider those combinations as don't cares, okay. So that is the one assumption we are going to make. Now, so after writing the truth table, next step is to obtain logical expressions for all the output variables. For each and every output variable, so we will be having expression. Therefore, so we are supposed to obtain logic expression for each and every output variable whatever we have. So finally, we are going to draw the circuit. Yes. So these are the 6 steps we have in design procedure of a combinational circuit. While designing a combinational circuit, so we are going to start from reading the problem statement, whatever the problem statement is given. So we are going to refer to it and we are going to identify the number of inputs, okay, and number of outputs which are required in order to realize that, and then we are going to assign some variable names to those inputs and outputs. Next, after assigning, we are going to write truth table. Truth table, so is a table which will be consisting of all the possible combinations of inputs, and so outputs also, for corresponding inputs will be having outputs. So we are going to assign logic 1 or logic 0 according to the problem statement. Whatever the output we desire, according to that we are going to assign values to the output. Okay, and then finally, so we are going to write the logical expressions. Each and every m variable will be having, okay, individual expression for each of it. Therefore we are going to write all the output expressions, okay, expressions for all the output variables, and then finally we are going to draw the logic circuit. After understanding the combinational circuit, what is the combinational circuit and what are the steps we follow in order to design a combinational circuit, we need to consider the design considerations what we have while designing the combinational circuit. The practical design considerations for okay, the combinational circuit are, the very first one is minimum number of gates. Okay, next is minimum number of inputs. Okay, next is the driving capability of each gate. Okay, then minimum propagation delay, okay, and the last one is minimum interconnections. Yes. So these are the practical design considerations we have while designing any combinational circuit. So first one is minimum number of gates. So our objective is to reduce as many number of gates as possible, because when we consider the ICs, okay, we need to have an optimized we need to have a circuit which is optimized in terms of the number of gates, because it is going to affect the area, it is going to affect the performance. So therefore we need to concentrate mainly on reducing the overall number of gates. Okay, therefore we need to see that the gates are less without altering the function of the combinational circuit. That is our objective. Okay, that is the first consideration we need to make. And next is minimum number of inputs. So minimum number of inputs to each gate. So even if you reduce one input to any of the gates, so that also reduces the overall area, the overall cost. Okay, so it is going to affect on all the parameters of an IC. Okay, the IC circuit. Therefore, so the second consideration we have is minimum number of inputs. The next one is the driving capability of each gate. So we need to consider this also, because simply we cannot connect n number of gates to any of the output. So any before connecting any of the next consideration what we have is the driving capability of each gate. So driving capability in the sense, so the output current whatever we are going to get from a gate. So we should see that the number of gates what we connect to the output of any gate is such a way that, so it is the output whatever we are obtaining, output current whatever we are getting from the gate is sufficient to drive those gates. So we need to look into that also. Next consideration we have is minimum propagation delay. Minimum propagation delay, yes, as I said, so the main aspects we consider while designing any of the chip is the speed, okay, then we consider area, then power consumption, etc. So when we consider speed, if you want to have a very high speed circuit, then we need to reduce all the delays whatever we have in the circuit. Therefore, so the propagation delay is one of the major delay what we have in a digital logic circuit. Therefore, we need to see that we have minimum propagation delay. So propagation in the sense the time taken by the signal to transit from input to the output, okay. So that is the propagation delay we have. So we should see that the delay is less. And the last consideration we have is minimum interconnections. So minimum interconnections, so interconnections are also going to contribute to the propagation delay. So we need to see that the gates are placed very close to each other so that the wires or the interconnections what we have are less, or the length of the interconnection is less. So wherever we have common connections, say for example when we design sequential circuits, so there also we come across this kind of problem. So where we may have to apply clock to so many of the different parts of the circuit, then we need to see that those are placed very close to each other so that the interconnections are reduced. So because interconnections are also one of the main cause for the delays what we have in the circuit. Therefore, in order to optimize any circuit, okay, any combinational circuit, these are the design considerations we need to make. Now, as an example of combinational circuit, let us consider adder and let us discuss so the design procedure what we follow in order to, okay, design an adder circuit. So adder is a combinational circuit which adds 2 bits, okay. So that is half adder. Actually, if you consider any adder, so it will be like, so we have 2 adders, half adder and second one is full adder. So this is a combinational circuit, so which is able to add 2 significant bits. Okay. Whereas the full adder whatever we have, it is also meant for adding 2 significant bits. Along with that, so it is going to consider one more bit, that is carry from the previous stage. So it is a 3-bit adder and it is a 2-bit adder. It adds only 2 significant bits and it is not going to consider the carry. So but full adder is a adder which is a 3-bit adder. It is going to consider the 2 significant bits, okay, as well as it is going to consider carry from previous stage addition. Okay. Yes. Now let us see half adder and full adder separately and let us understand so what are the different circuits we can have for half adder and the full adder. Okay. Yes, let me consider half adder first. So half adder, so we are saying or we are calling this circuit as adder. Therefore, so it should have 2 inputs and we should have, okay, sum and carry as outputs. Let me write, okay, all the possible combinations to this. Okay, since we have 2 inputs, so 4 combinations are possible. I have written all the possible combinations and now let me write the sum and carry outputs. So when the 2 inputs are 0, 0, sum and carry are 0, 0. When we have 0, 1, the sum output is 1, there is no carry. Next, when we have 1, 0, the carry is again 0, sum is 1. At last we have 1, 1, 1 plus 1 is 2, 2 is represented as 1, 0, in the sense sum is 0, carry is 1. Now let us write expression for all these outputs, okay. So I will write all the expressions, all the min terms and max terms. Later we will consider, okay, the different equations for sum and carry. So now if I write expression for all these 4 combinations, so in SOP form if I write, so for the first one, so what is the input we have? AB, therefore, so A dash, B dash are the inputs we are supposed to give in order to obtain. So in case if we have logic 1 here, so that is the expression we are supposed to use. Now next combination is A dash B, next is A B dash, last one is A B. And coming to the POS expression for all these, so let us write A plus B, next is A plus B dash, A dash plus B, last one is A dash plus B dash. Now let us write expression for sum and carry. I have written all the possible combinations and all the possible expressions. Now let us write particular equation for sum and carry. So if you observe sum, so you can notice we have logic 1 in 2 places. So one is in the second row, the next one is in third row. Therefore let me write SOP expression first, later we will go with the POS expression. So if you consider the SOP expression, see, so we have logic 1 here, therefore A dash B plus A B dash is the expression, whereas for carry we have A into B as the expression. So now this is the first equation whatever we have obtained. And now if you observe carefully, you can notice that this carry is representing AND gate, because in AND gate, so for all these combinations, input combinations, we are going to get the same pattern output, because in AND gate we know that the output is logic 1 only when both the inputs are 1. Therefore, so the carry can be replaced by an AND gate, and this, and there also we have an AB, so which is nothing but a AND gate. And if you observe carefully the expression for if you observe carefully the truth table, whatever the entries we have for the sum, so we can represent this by a XOR gate. This is the the output pattern whatever we have for sum is same as the XOR gate output. Therefore, another expression for the sum is so A XOR B, and for carry the expression remains as it is. So now let me represent circuits here. So let us consider we have complements are available. So by considering that, so we can represent this as so A dash into B. Another AND gate is required, 2 AND gates and 1 OR gate is required here. Here we have A B dash, A B dash, and finally we have some expression here. So if I write circuit for this, so it is very simple. So we have A, B which are given to XOR to obtain sum, and the same inputs are given to carry. Yes. So these are the 2 circuits we have. Other than this, so we can have another 3 circuits for half adder. So in order to give the options for a designer, so we can go for any of the circuits, any of the equations whatever we have here. Let us see all the equations. Yes, now we have 2 equations. And if you consider the POS form, so this is for SOP. Now if you consider POS, so before that, so what we can do is we can have another representation for this. See, sum is represented as A XOR B, right? So this can also be written as, see what I have written, which is nothing but A X nor B dash. I have used both bar as well as dash here, so which is one and the same. But see, observe here what I have written. So this is nothing but the complement of X nor, so the 2 complements if cancel, then I am going to get XOR itself. So another way we can write this as A dash or AB plus A dash B dash is X NOR, okay, X NOR whole dash, and carry will remain as it is. So for this, if I represent, so we require 2 AND gates. For one we have AB as input, for another we have A dash B dash, okay. These are given to OR gate, and at last, because we have whole complement, so at last we need to consider a NOT gate, and see here, so sorry, I have represented it as XY, so we can have XY also as inputs. So since we have considered AB, okay, as inputs, let me write AB itself. Yes, C is equal to AB, and if you observe here, see, AB is available here, so I can represent like this. So using SOP, these are the 3 different circuits we can have, okay. Now let us see for POS, so what are the circuits we can have. Therefore, so he say here, since I have AB which is nothing but carry, so this can also be written as S is equal to C plus A dash B dash whole dash, okay. You can write this as C plus A dash B dash whole dash. So these are the possible equations. So any designer who wants to, okay, use any of these equations, so can be used while designing any of the circuits which require an half adder as a part of it, okay. Now let us see the POS expressions and its circuits. So yes, for some using POS, see here we have logic 0, here we have logic 0. So what is the expression we have? We have A plus B, okay, and A dash plus B dash. For carry, so we have logic 0 in 3 places. So we do not prefer, because it is going to increase the number of gates. So if I write the carry expression in terms of POS, then it requires 3, okay, OR gates and 1 3 input OR gate. So it is going to increase the gates, therefore just, okay, I am going to write AB itself, okay. Yes, now if I draw the circuit, so it requires 2 OR gates, A, B, another is A dash, B dash. So if I give this to AND gate, I am going to obtain sum, okay. And for carry, same representation. Yes, the carry can be represented like this. Let us retain sum as it is. So carry can be represented using De Morgan's. See, so if I expand that, so we are going to get A into B again. So for this, if I draw the circuit, so A or B, A dash or B dash, this is sum A, B, A dash, B dash. A dash plus B dash is available here. So here it is A plus B, it is A dash plus B dash. So just we need to use another NOT gate in order to obtain carry. Because already A dash plus B dash is available, just, okay, if you use a NOT gate, it is going to give you A dash plus B dash whole dash, which is nothing but AB. So all these circuits can be used, okay, for half adder. So depending on the whichever the signal is available, so we can go for any of these circuits. Yes, after understanding all the possible circuits for half adder, let us see the full adder circuit and let us understand, so how to write the full adder truth table as well as the circuit. And in full adder, so we have one more variation, that is, so we can represent full adder using 2 half adders. Let us understand, so how to represent or how to write the truth table, the circuit for full adder first. Later we will see how to realize full adder using 2 half adders, and we require one more additional gate in that, that is OR gate, okay. Let us see full adder. So in how to represent the full adder, as we discussed earlier, so we are supposed to represent as a block, okay. So the inputs to full adder are A, B, C in, or you can consider just C, okay. So on the other side we have sum and carry out. So we have A, B, C in, or you can consider X, Y, Z, okay, and S, C for this, and this is represented as full adder. The block, okay, is represented as full adder. So this is the representation of the full adder. Now let me write the truth table to this. So we have A, B, C in and C out and sum, okay. Yes. How many inputs we have? We have 3 inputs. So possible combinations are 8 combinations. 5, 6, 7. Okay. Now coming to C out, both are 0, 0. Yes, here we have sum as 1, carry as 0. Again, sum is 1, carry is 0. 0, 1, 1. 0, 1, 1. 2. 2 is represented as 1, 0. Next is 1, 0, 0. So again 0, 1. Next we have 1, 0, 1. 1, 0, 1. So output is 2. 1, 1, 0. Output is 2 again. And at last we have 1, 1, 1. Output is 3. So in binary we represent 3 as 1, 1. So these are the inputs and these are the outputs and these are the logical values. So the truth table for full adder is ready now. Now let us write the expression for the sum and carry. So in order to write the expression, okay, so you can refer the logical ones and logical zeros and then you can write, or else you can go for the K map. So K map is a corner map, so which is a graphical representation of these values. We are going to use K map in order to reduce the expressions. In order to reduce the Boolean expression, that is one of the tool we have. So let us, okay, enter these values into the K map and let us obtain the expression. Okay, so I will show you both. So I will write the expression from the truth table as well as we will write the expression from the K map. So let me write the expression from the truth table for sum and carry. For sum, so we have logic 1 here, here, here and here. Okay, yes. So if you observe the input whatever we have 0, 0, 1. 0, 0, 1 is nothing but A dash, B dash, C in. Plus next we have 0, 1, 0 which is nothing but A dash, B, C in dash. Next we have 1, 0, 0, A, B dash, C in dash. Next we have A, B, C. If you observe carefully, okay, so we don't have any, okay, two terms which are differing in one literal, so we cannot reduce further. Okay, so we can have another representation but we cannot reduce further. Okay, yes. Now let me, okay, so write the K map for this. So how to write the K map? K map is written like this. So if we have a 3 variable, then this is how we are going to write the K map. It will be having 8 cells, okay, and MSB is written here. I can write, okay, the LSB here. And for one variable we can have either 0 or 1, okay, we are going to write 0, 1 here, and 2 variable combinations are 0, 0, 0, 1, 1, 0, 1, 1, but we are going to change this order. We are going to use gray code because in order to reduce any expression, okay, we need to have 2 terms which differ by 1 literal. So they should have logical symmetry, okay, therefore so we need to reduce. If you want to reduce, then you need to have only difference in 1 literal, then only we can reduce. For example, so if we have A, B, C in as 1 literal and another literal is A, B, C in dash, okay, then we can reduce. We can take out this as common, A, B as common, and C in plus C in dash will become 1. Therefore, we are going to get A, B. So we have reduction in 1 literal, 2 terms has been reduced and we have only, okay, so a literal containing 2, okay, variables. Now, so therefore, so what I mean to say is here, so if you write 0, 1 and 1 0, and if you observe, so these two are differing in both the places, both the literals are different. In such case we cannot reduce. Therefore, since K-map is used for the reduction purpose, remember while writing K-map we are going to write the values like this. While writing the values itself, while writing the adjacent cells, okay, values, we are going to write in such a way that they differ by one literal, or simply we are going to use grey code instead of binary. Okay, yes. So this is the way we write the values for the variables. Now let us write the entries. 0 0 0, in that row we have 0 as the entry, 0 0 1 is 1, 0 1 1, 0 1 1, sum is 0, 0 1 0, sum is 1, next we have 1 0 0, sum is 1, 1 0 1, sum is 0, 1 1 1, sum is 1, next 1 1 0, sum is 0. So these are the entries we have. Now in order to reduce further, we need to have adjacents, okay. The logic ones whatever we have, they must be adjacent to each other so that we can make groups. So in K-map we are going to reduce by making groups of cells. We can go for 2 groups, we can go for 4 cell grouping, we can go for 8 cell grouping, okay, that depends on the K-map, okay. Yes, now we have maximum we have 8 cells. So if you have logic ones in all the 8 cells, we can group, okay, we can go for a 8 cell grouping, or just we need to check whether we can make group or not. If you observe here, so we cannot make any group here. Carefully see. So we don't have any 2 adjacent cells which contain logic 1. Therefore, so we cannot group like that. So see here. So since we cannot do further reduction, we need to write expression for each of this. So if you write the expression for each of the cells, then we are going to get the same sum expression. So further reduction is not possible. So coming to the carry, okay, let me write, yes, so expression from the truth table. Later we will see, okay, what is the expression we are going to get from the K-map. Yes, here we have logic 1. So here A dash B C in plus we have A B dash C in, A B C in dash, A B C in. Yes, see here. So if you observe carefully, here itself we have a possibility for reduction. So we have A B C in, A B C in dash. Just now I show, okay, previously I showed the same, okay, combination, same literals, okay, I have taken, and so I have shown you how to reduce. Therefore it is possible to reduce here. So let us take the aid of K-map in order to reduce the carry expression. So let me, okay, write K-map for carry. MSP is written here, okay. These are the next 2 variables. Entries are 0 0 0 1, 1 1 1 0. Here we have 1 0 0 1. Now let me write the entries 0 0 1 0. You need to read, okay. 0 0 0 we have 0. Next 0 0 1 we have 0. 0 1 0 we have 0. So 0 1 0 is 0. So 0 1 1 is 1. Like that you need to check, okay, and enter these values. So if you copy the truth table entries into the K-map, so that is how it looks. Now let us see, so the grouping. Here if you observe, so the maximum grouping possible is 2 cell grouping. We have 2 adjacent logic ones here, okay. You have 2 adjacent logic ones here. Again 2 adjacent logic ones are here. So if you observe, this cell has been repeated 3 times. So that's not an issue. You can repeat any number of times in order to reduce further, okay. Now so we need to learn how to write the expression. So first group whatever we have made is this one, second group is this one, and third group is this one. Let me write the expression for the carry, okay. So by writing equation for these 3 groupings. So if you consider the first one, so how to write the expression now? We need to see the common variables to those 2 cells. Here we have logic 1, here we have logic 1. So we need to carefully observe which are the common variables we have for these 2. So that is the expression for that particular grouping. Okay. Yes. So we have here logic 1 and here logic 1. If you observe the MSB, here it is 0, next it has changed to 1. Therefore, it is not common. So we cannot choose A here. Now let us move to the other side. So that is we have B and C in. If you observe, B and C in are 1 1 for the first, okay, row, and it is same for the second also. Therefore, the expression for this is B into C in. Okay. Next, let us consider the second grouping. Here we have, all of you observe carefully, here we have logic 1, and here this variable A is common for all the 3 cells. Okay. Not only all the 3 cells, or for all the 4 cells, A is not changing. A is fixed. Therefore, for this as well as for this, A is one of the common variable. So, A is one of the common variable. Now, let us move on to the top, okay, to the other side. Here if you observe, see, B has been changed from 0 to 1, but C is same as, C is remaining same for both. Therefore, A into C in is another expression. So, last one, A is common again for these two. On the top if you observe, B is common. So, AB. So, if I rearrange, AB plus BC in plus AC in. Yes. Now, let us see the realization of these two. So, sum, how many gates are required? So, since it is not reduced, so we require, okay, 4. Three input AND gates and 1. This is sum. So you need to write A dash, A dash B dash C in, A dash B C in dash, A B dash C in dash, A B C in. Okay. So this is sum, okay, realization, and carry we have A B C in A, this is carry expression. This is the realization. Okay. Yes. Now, so this is one way of representing sum and carry. Now let us see how to represent the full adder using 2 half adders. Okay. Yes. Let us consider same sum expression here. Okay. So, as I said, it cannot be reduced further, but it can be represented in another form. Yes, let me consider, okay, yes, here, so which are the common or which can be taken as common here, A dash, only A dash can be taken out here, A dash, B, C in dash, plus here we can take out A, this is B dash, C in dash, plus B, C in. Further, this can be written as A dash B XOR C in plus A B XOR C in bar, B X NOR C in. Okay. Yes. Further, if you observe, it resembles A dash B plus A B dash. It resembles A dash B plus A B dash. So, it is nothing but XOR gate again. Therefore, considering this as single variable, we can represent this as A XOR B XOR Cn. A XOR B XOR Cn. Okay. Now, so from this, so what we can have conclude? So the sum is a output of XOR between, okay, see here, XOR between A and XOR output of B and Cn. Therefore, so for the first gate we can give B and Cn as input, okay. The output of this can be given to the another XOR gate which accepts this output and A as input. Or so instead of writing like this, we can write like this, A XOR B XOR Cn. So we can have A XOR B output, and that output can be, okay, XORed with Cn in order to obtain sum. Now let us consider carry expression, okay, and let us see, because we have seen earlier, so how to represent carry in one way. Now since we are going to realize, so using full adder using two half adders, so let us see how carry can be represented or carry can be realized in this case, okay. Yes. Now, so carry expression we have is A dash okay see here I can take Cn outside and this can be written as A dash B. So these two can be simplified and written as AB. So this can be written as A XOR B. Yes, this is the expression, simplified expression for, okay, the carry out, C out. So I have not represented, okay, just I have represented as C. So we can represent this as C out also. Yes, so now we have new expression for this. Now let me write two half adders, okay. This is one half adder. Okay, so I have written two half adders here. Half adder 1, half adder 2. Okay, yes. Now, if you observe, as I said, so A and B can be given here. Okay, here we have A XOR B. So this can be connected to the next half adder, and so to that the another input will be Cn. So here we are going to obtain A XOR B XOR Cn. Okay, this is the sum realization. Coming to the carry, here we have AB. Yes, see here, which is a term required. Next, see here, we need to AND between A XOR B and Cn. So if you observe here, here we have A XOR B and here we have Cn. Therefore, so here we have AB, here we have Cn into A XOR B. Therefore, so the terms which are required to realize C out are available, but only the thing is, so we need to use additional logic circuit or logic gate in order to complete the realization. So that additional logic gate required is OR gate. So the output, that is the first term we have here, second term is available here. If you give these two to OR gate, we are going to get the C out expression. So this is how we realize full adder using 2 half adders and 1 OR gate. Okay. So that is all about the combinational circuit and adder example what we have in the basic electronics. Thank you.